is what we'll talk about today, and I showed you that kind of in the lab and showed you how things try to oppose the changes we apply to this equilibrium system. So when a chemical system is at equilibrium, disturbed by a change in one of its properties, the system responds in a manner that opposes this change. There's a three-stage process involved in this. So when you start out, you're at equilibrium. Okay? Please note that when we start with the two gas tubes, okay, well, the first one anyway, that was kind of in that box, that's at equilibrium. And then I'm going to apply a change to it. It's not going to be in equilibrium anymore. So it's going to cool down, for example. I put it into the cold ice bath, and it's going to cool down until it reaches that specific temperature, maybe, I don't know, let's say 4 degrees Celsius or something along that line. And once it reaches 4 degrees Celsius, it's going to reach another equilibrium, resulting equilibrium. So it's a three-stage thing, and usually we have graphs that represent this taking place, and that's what we're going to look at today. LeChatelier's principle is used to predict how an equilibrium system will respond to a change imposed upon it, right? So if we change concentration, I did that today. I added water to it, so I changed the concentration of the water that was in that system, okay? Adding in a chemical favors the reaction that uses up that chemical. If I put in H2O, I got to use up that extra H2O, okay? So if I put in chloride, I got to use up that chloride, all right? If I take out a chemical, so we didn't do that in the lab because it's kind of hard to pick out the chloride ions, yes? It's kind of hard to take out just the water, okay? But if I take out a chemical, it tries to replenish that chemical, okay? So if I take something out, it's going to try to make more of it again, because it's no longer in that equilibrium system, okay? So we take a look at this one here, for example. We're going to have some graphs that go with this, and this is kind of the important part coming up here. If we look at the formation of HI, this is an equilibrium system here. H2 plus I2 gives me 2HI, all right? What's going to happen if I add H2? What is this going to look like? So let's take a look here. Just bear with me for a second here. I got to kind of put in the stuff that you guys have there. This didn't all transfer over. Okay, so we had some H2, I2 it says on yours there, and some HI gas. And what I want you to understand here is you'll see this is the initial equilibrium state. So the first little chunk there is the initial equilibrium that we're at, all right? The second thing I want you to understand is that this is concentration here, yes. It does not mean we have three separate things going on here. So we're just put it on the same graph to represent this. Please know that this isn't the highest concentration, this isn't the middle, and this isn't the lowest. That's not what we're saying here. If you look at those, we got kind of three separate graphs. So we got this section here for this one, we have this section for the I2, and we have this section for the HI kind of thing, okay? So that's all I'm saying. What would happen to these concentrations? Would they go up? Would they go down, et cetera, okay? If I add in H2, what's going to happen? Well, the first thing that happens, and this is important, the first thing that happens is when you add in H2, you get a large amount of H2. So we represent that by doing this, straight up here. So we're going to add in some H2, okay? So the concentration is going to basically spike, right? It's going to go up very quickly. Here's my equilibrium system. I dump in a bunch of H2. The concentration of H2 is going to go up. But once it goes up, what does LeChatelier's principle say? I have to what? I have to use it up, yes? So what is that going to look like as far as the resulting equilibrium? Well, it's going to spike up some amount, and then it's going to start to get used up until it reaches equilibrium again, okay? In order to use up that H2 that I just did, okay, let's go back to the equation here, guys. Look at my equation. I put in a bunch of H2. I need to use up the H2, right? That's what LeChatelier's principle says. Put in a bunch of H2. I need to use it up. If I'm going to use up H2, I have to use up I2 as well, right? because otherwise, how am I going to use up the H2? How do I get rid of the H2? I have to make HI, yes? So if I use up H2, I got to use up I2 as well. All right, so what does that look like? Well, we don't have to represent the spike in this case because the concentration of I2 didn't go, I didn't add any I2, I didn't take out any I2. It starts right here and it just simply gets used up. So it's going to look something like that, okay, until it equals out, okay. Now, if I'm using up H2 and I'm using up I2, in other words, to consume that H2. So if I'm using up this and I'm using up that, what's going to happen to HI? I'm going to make more of it, right? It's going to go up. So I got to represent that by this graph here. And so we'd start here, of course, and we would kind of go up like this. Okay? Now, does it go above the I2 concentration? Probably not, but it really, there's a lot of factors involved there, but that would be just perfectly fine there. This is just a rough graph. Obviously, we don't have any numbers along the side here, so I can't tell you exactly where this is going to end up and things like that. That's not the point. This is just a rough graph. Now, notice there's 3 different stages, like we talked about. There's 3-stage process. This is your initial equilibrium, so everything's happy, happy, happy here, as Phil would say, yes? And then we have a non-equilibrium part. That's where it's trying to adjust itself. It's trying to get back to equilibrium, right? That's where I dump in a bunch of H2 and it spikes up. And then it says, hey, I'm not happy about this. I got to use that stuff up. So I'm trying to get back to equilibrium. That's that non-shifting or non-equilibrium state there. And then finally, we get back to equilibrium at some point. It's probably not going to be the same equilibrium it was before. That's okay. But it is going to get back to an equilibrium somewhere, okay? For example, if we, I added in the, let's do the water one because that's the obvious one. We add in water and it turns really pink. Is it going to stay really pink or is it going to go back? It's probably going to stay fairly pink because I've added in quite a bit of water. But that is now at an equilibrium, okay? That's a new equilibrium that it's reached now, okay? And then let's take a look at what happens if I take out HI. So if I take out some HI. So let's do another graphy here. Once again, just bear with me for a seckie. Okay, so I'm going to take out HI. What's going to happen? Well, I'm going to remove some of it. So if I remove some HI, the first thing that's going to happen is I'm going to, if I start right there, for example, this is my HI equilibrium, it's going to decrease in concentration very rapidly. I'm going to take out a chunk of HI. I'm just going to take it out. So what happens to the concentration? Well, it's going to go down. I'm not going to have as much anymore. But if I take out HI, what does it try to do? It tries to make more, yes? So then it's going to try to increase back up again. And once again, it's probably not going to reach its original equilibrium, but it's going to try and make more. Okay. How does it make more? Well, there's only one way it can make more HI, and that's to use up H2 and use up I2. All right? There's no other way to make more HI than using up those 2 reactants to make more HI. Okay? There is numerous things you could do to this, and industries will use this as well. I mean, this is only going to be good until you use up all the reactants, of course, but could you think about this? If I want to make more products, I'll take some out, right? If it's in an equilibrium, I'll take out some products, and I'll get more products, right? That'll work out well. Of course, you got to be careful here, because eventually these concentrations would probably, at some point, deplenish enough, or basically they'll get so low that it won't be able to do that reaction anymore. It'll probably actually end up going back the other way again. So there is obviously a little bit of that going on, okay? And once again, you got your 3 stages. So we have our initial equilibrium, we have the changing part where it's not at equilibrium, and then the resulting equilibrium there, okay? So take a note here. This is we're going to talk about this over the next 2 days, including tomorrow as well. The value of Kc is not affected by the addition or removal of a chemical. So if you add or remove something, that value of Kc does not change. Okay? Does not change. Now we're going to talk about changes in temperature, and once again we saw this in the lab here today, but let's talk a little bit about this. Okay. Now we talked about, you know, I kind of showed you this is an endothermic one, this is an exothermic one, but basically once again LeChatelier's principle says it's going to oppose that change. So it says here, if you heat up the system, well, what's the opposite of heating up the system? If I heat up this system, if I put it into a hot water bath, it's going to try and cool back down, right? So it would favor the endothermic part of that, right? There's a couple ways you can think about it. You can just think simply, if I heat something up, it's going to try and cool back down. That's the endothermic reaction. That's cooling down is endothermic, right? The other way to think about that is, if you remember the second example we did, we had plus energy at the end. Well, if I give it energy, it wants to use up that energy, right? So if I put energy into that, if I heat it up, it's going to try and use that energy to cool back down again, okay? So it's going to try and consume that. Of course, it's going to become endothermic. Heating up the system is endothermic. If I cool it down, it's going to try and heat back up. That's exothermic, okay? So you have to keep that in mind. So we take a look at this example here. Now, if you're keen, and you know what, if you kind of pay attention to the lab today, we know that we already know this, yes? Although technically in the lab, just so you know, it's the opposite. I wrote this one backwards, okay? The lab that we did was switched around here. Now, you probably, okay, we're going to talk about this one, and I'm going to tell you what we're going to talk about. Sorry, on the next sheet here, it says, or you guys can see that right below, it's going to talk about heating up the system. If I look at this, and I say, let's heat up the system, what's going to happen? What do you think is going to happen? Do you know? If I heat up this right here, do you know what's going to happen? Well, in this one you may know, but what if I give you a different reaction? Then what? We did this one in the lab here, so that's kind of cheating for you guys. I'm not going to give you this one again, of course. But how would you know? Don't know. How could you figure out what's going on here? What do you need to do, guys? N2O4 goes to NO2. What kind of reaction is that? Could we figure that out? How? How? Yes? No? How? No idea. Yeah. Yeah, but what if we don't know? What if I give you a totally different reaction here, and you don't? Well, this is all I give you, so you don't know if it's changing color or not. What? Huh? What about the data booklet? How are you going to tell? Unit 1, guys, come on. Unit 1. Nope. Unit 1. How are you going to figure out if this is an exothermic or endothermic reaction? How could you figure that out? Yeah, and how would you do that? What? No, not specific. I think you got the wrong term there. Heats of formation. Hess's law. Yes? So, down here, I want you guys to do this, please. Now, like I said, we did this in the lab, so maybe you guys can figure this out, but I want you guys to write this down, please. So, products minus the reactants. All right? That tells me delta H for this particular equation. If I figure that out, I can tell you if it's an exothermic or endothermic reaction based on whether it's a negative value or positive value. So I had NO2, that's nitrogen dioxide. So I'm going to go 2 times NO2 for the products. NO2, nitrogen dioxide, is a positive 33.2 kilojoules per mole. And I got 2 of them according to this equation. Okay? That's my product side. And reactant side, I have N2O4, and only got 1 of those. So minus 1 times N2O4 dinitrogen tetroxide, which happens to be a positive 11.1 kilojoules per mole. Okay? And if I subtract those two, delta H here, that's what? 66.4 minus 11.1, which is what? 53.3? Positive, yes? Is it 53.3? 55? 55.3 kilojoules, yes? 55.3, is that right? Okay. 55.3. So now, after you've done that, okay, because look guys, like I said, we did this in the lab and that's okay. Just forget about that for a second. What if I give you a different equation? How are you going to know if it's going to say, here's the equation, I'm going to heat this up. What's going to happen? You have to find out delta H so that you know, is it exothermic? Is it endothermic? What happens when I heat it up or cool it down? Okay? This is a positive 55.3, and I just finished telling you that this was the products here, right? This is the reactants, and of course, guys, when we read this equation, yes, it's an equilibrium, it goes both ways, but we read it left to right. So going this way, that's my products, that's my reactants. I would say right here is delta H is a positive 55.3 kilojoules, and I want you guys to write that in there, please, at the end. Delta H notation, a term at the end of the equation. Because that's a positive 55.3, that means that's an endothermic reaction going this way. Yes? True? Right? Positive 55.3 means that that's an endothermic reaction going that way. Because now that I know that that's endothermic, I know now that if I want to flip this reaction around, this of course would be exothermic. And you're going to put those above and below every time. Okay? You have to do that so that you know which way is endothermic, which way is exothermic, what's going to happen if I heat it up, what's going to happen if I cool it down. Okay? So do that now. Put endo up here, put exo down here, please. All right? Now that you know that, you can continue with this question and figure out what's going to happen here. And if you look back at the lab, by the way, like I said, I had these two switched around. So actually, I told you over there, delta H was negative 55.3 because, of course, those two were switched around, which makes sense. Okay? So you're always going to do that. If it doesn't tell you the delta H, you have no way of knowing whether the forwards reaction is endothermic or the forwards reaction is exothermic. And once again, they obviously could be endothermic or exothermic, and it could be endothermic or exothermic going this way. So it depends. Make sure you know. Now that I know that, I can fill in this chart here on your first one, which says what happens if I, let's see here, I think the N2O4 is up here, isn't it? Is that right? And the NO2 is there. And I think the first one is if I heat it up, correct? Okay, so if I heat it up, what's going to happen? Well, let's take a look here. If I heat it up, okay, I need to cool it back down, yes? So which reaction is favored in this case, forwards or reverse? Which reaction is going to be favored, forwards or reverse? I'm heating it up, I need to cool it down. Forwards, yes? Because that's the endothermic one. So if I'm heating it up, it's trying to cool back down. I'm going to be making, look, it's going to go this way, right? I'm going to be making more NO2. To make NO2, I need to use up N2O4. So I'm going to be making more NO2. Okay? Making more product favors the forwards reaction. And I'm going to be using up N2O4. Okay? There's no spike with this one because I'm not taking out or adding in any N2O4. Like, you think of the gas tube. Did I put any more gas in there? No. Okay? That's exactly what this is. I just heat it up and I cool it down. I didn't put any more gas into there. All right? they're sealed, so that's pretty tough. Okay, and once again, you can see the different states here. Let's take a look what happens if I cool it down. Well, once again, if I cool it down, we look at this reaction here, and I say, if I cool it down, I need to heat it back up. And if I want to heat it back up, that's an exothermic reaction. So now it's going this way. It's going to favor the reactants. I'm going to be making more reactants. So I'm going to see an increase of N2O4 and a decrease of NO2. Okay? So I'm going to decrease NO2. And I'm going to, I probably should use maybe a different color for that, NO2. And I'm going to increase N2O4. Okay? And that's what basically LeChatelier's principle says, is that for any change that we apply to it, it's going to try and oppose that change, or basically do the opposite. You know, put in more water, got to use the water up. Take out water, got to make more water. Okay? So that's the kind of what we're talking about here. Changes in temperature always cause changes in values of Kc, because if you think about Kc and the relationship between the products and the reactants, and we talked about this yesterday, the products are on the top, the reactants are on the bottom. If I'm forcing the reaction to favor the products to the right, favors the right, I'm going to be making more products and using up the reactants. Kc number is going to go up. More up here, less down here. Goes up. Vice versa. If I'm going to favor the reactants, so if I'm going to shift it to the left, I'm going to be making more reactants and less product. So small over large, Kc value is going to go down. Okay? So that's what it talks about on these two there. Okay? And that's the last thing there. All right. Any questions, anyone? Okay. We have a worksheet for you here today, of course.